Hello, everyone. This is Professor Ma, and this is the brief introduction to the sections on elementary formulas and basic graphs. What this section is basically how formulas are built, and also some examples of the graphs of which we have absolutely have to know before we're going to use a lot in the class. Okay, so a brief review on that. So these are two basic topics. The family of basic family of formulas and how we make more complex ones, and then the pictures, basic pictures. Okay. Uh, of a long formula such as these, and if I take a look at it and follow what happens if I were to plug in a number, is zero. Okay, if I take a zero, I stick into the x, and I stick into the x, and what it goes through, calculate what 2x plus 1 is, and that's 1 on top, and the sign of 0, 0, that's 1, so I get log of 1 divided by 1, then finally I get 0. Okay. Uh, so how a complicated so formulas such as these are typical formula in science. How are they made? Well, they basically made up of numbers multiplying to the letters variables. Then we use plus minus the operations, arithmetic operations, and then we use different family of functions, formulas, and basically there are three formulas, and these are the three formulas that usually shows up on scientific calculators, and I blocked out for you, and those are the trig formulas right here, and these are the logs and exponential formulas, and then these usually we use for the power functions, okay, and here's some, and the inverse, of course, and these are the, what we loosely called basic formulas. Okay, there's three families: the algebraic family, trig families, exponential families. Okay, we went. That's why we went through them in the previous sections. Okay, so these are algebraic families, and the word algebraic basically means that if I give you a number x, it's reasonably that I can calculate with these numbers. Like taking square root or half power, and that's doable. And that a number I can take the cube root that's can be calculated by hand. That's what the word algebraic refers to. And these are all algebraic formulas. And the most important uh, class of algebraic formulas, of course, are polynomials, and they are these forms in the fractions. The fractions, which are called rational formulas. Okay, so these are examples of rational formula polynomials, and roots are not polynomials. Okay, with those we call power formulas in this class. Trig formulas, in the inverse, and of course, and that how do we make complicated formulas? Now, basically, we make them by what we call compositions. That is, we input a formulas into another formula. Okay, and for instance, if f of x is sine of x, g of x is squaring, then if I feed my x into, using this notation, f first, that's what inside first, f of x, and then I will wind up with sine of x. But I'm not done yet. I'm going to immediately take this output and treat it as input. I'm going to feed it into the formula G. G, of course, will square everything. Here we use a formula X, letter X, but what it means is a general letters. That's what we meant that by that X is a general uh, variable. It could be any variable. If you cause confusion, if you like to use the variable u, so we'll call the sine of x u, then I'm squaring the u, and of course I will have u squared, which is sine x squared. Or we'll put a square over here. Okay. So we'll wind up with what I should call a two-layer formula. Okay. I mean, I will use that phrase, meaning it goes through two families, and one of families, each family, the formula sine x is very clear what is being done to the x, and then the squaring, it's very clear what's being done to the input. You square the input, but when you finish, you wind up with this two-layer formula sine of x being squared. Of course, I can make a three-layer, four-layer, five-layer. Now you got the idea. I can make different layers added to other formulas in different layers, then feed into, and so I can build complicated formula with compositions and the algebraic operations. Okay. That's what it's about. And here are some examples how the x's went, when you give an input, what each functions is invoked from which families. The basic one, you take one of these and that you put the x, feed the x into it, then you take the result, maybe you add them, and then you take that and you do something else, etc., etc. So this is a breakout, some of the breakout of the flowchart you like. Okay, so 2x squared, algebraic cosine x, I'm going to add them. Then I'll wind up with these additions. Okay, then we're going to take that formula as an output, as an input into the log. Okay, so now then this now is a kind of like what is a two-layer function? Now, if I take log of this, feed into something else, that will be what I call a three-layers. Yeah, here's a kind of like three-layer functions. We'll have to take the things we got before for the numerator, log of blah 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 blah, log of which is a two-layer formulas, and the bottom one is two-layer because I feed the x into sine, the sine x then fed into the exponential formula. Then I add some numbers, okay, if you like, and then I make a fraction out of it, and after that I feed into the square root formula. Okay, so this is the entire flowchart of these formulas, how it is, what the x go through when it is entered into the formula, what has to be calculated, which one first and which one second, and how do we compile all the each individual answers into a bigger and bigger final answers in detail. Okay, and this is one way, one decomposition, if you like. Okay. This is important because later on, when we do an operation called derivatives, we need to know the structures of this complicated formula in order for us to go to extract something called its derivatives based on the structures. Okay, and here's some example how this for deconstructing formulas. Okay. We also use this circle operation, which we call compositions operations, with a little circle. And the way to read this circle is this part, whoever is closest to the x. Okay, reads from right to left. Okay, x is being fed into that one first. Whatever comes out then is fed into that one. So G circle f of x, and viewing as an assembly line, kind of backwards. So this x is here, and it's fed into f, and then I get f of x. Then f of x is fed into g. Then I get g of f of x. And if I have another formula h, then I will get h of x. Yeah. And I have to keep track of parentheses. You type this into calculators, and a calculator, they will understand that. Except if you miss a parenthesis, and they might say, no, something wrong here. If there's h here, then of course h goes here. Then we'll put a circle there. Okay, if there's an h there. Okay, so you keep linking out. So it's like assembly line, x being fed into this process, and then that process, however steps of process, which, and which formula process the previous output. So we circle them, okay? And so these are some examples of what it turns out to be. Okay, you can decipher that. And here we do it backward, break it up. So here's a two-layer functions, and the inside layer, that is the 9 plus x squared. Okay, we call this the argument in mathematics. So the arguments, and this in the future notation, we will use the letter U for the arguments in a lot of process in the future. Okay. You will see the letter U, and it serves in a lot of context. It serves as the argument, that is the things going to be put into the formula. In this case, it's 9 plus x squared. Okay. So the argument, if you like, U is 9 plus x squared. Okay. Of x, f of x. Then g of x is sin of x, and then this is g circle f. Because we feed into the f first, then the outcomes fed into g. Okay, so these are more examples how things breaks up, so you can think about it. Okay. Now, then what else? So you will see, you will encounter a lot of situations which basically what you are doing is you're breaking up the process later on, but it doesn't have to be in this detail written out, but the manipulations inside the head or the pen with the that's what's being happening. That's what's happening. It's like you doing that. What else? Then what are the basic graphs we need to know? Here is a picture of what I call a Joe Blow graph in calculus. That is standard graph pictures, and that is we have some formulas and y to f of x, and I have some Joe Blow points x and where it is corresponding on the graph. Okay, and in the picture, basically trying to point out, x can be generic x, but in one thing we need to emphasize is this y is always refers to how high it is. Okay, so there's a geometry. We're going to manipulate these pictures, symbols, pretty soon. Not symbol, these figures. What kind of graphs or going in or we need to know by heart? Here, first and second degree functions, y to f of x, linear in the second degree. So and these are reviews of how to graph them, lines of parameters. Okay, leave that as for you to go through. But there's a couple of things I want to talk about graphs, and there are things that we do to graphs that a couple of operations I want to mention. And one thing is the absolute value operation. A lot of time we take a formulas and y to f of x. And for one reason or another, we want to look at just the absolute value part of f of x. A lot of time we use these problems to create formulas that satisfy some conditions, some examples that we need. Okay. Then in the graph level, basically when we change, remember what I said about the f of x is the y component is the height. So if the y is the y component, if I slap the absolute value around it, then it's going to change it to positive. So in other words, these points can be graphed in the upper half because all the y value tend to positive. So the absolute value graph basically just take hold of the roots and flip all the negative parts underneath upwards. So you got these bouncing balls kind of like path. Okay, that's absolute value. That we will use that sometimes. And then we have these cut and paste operations. Okay, and a lot of time we need examples of formulas for which are artificially constructed to demonstrate something, and they're called piecewise functions in mathematics. Or actually, a better word for them is multi-rule functions. Okay, which piecewise or multi-rule. Okay, that means it's not defined by a single nice formula. It's defines the rules for the inputs for making the answer, for finding the output is depending on what number the number you put in. So here's one. It says, let me explain what this means. Okay, the rule number one is for if the number you put in there is bigger than 0, then the this is y, or y is equal to 1. So in other words, as long as you put x over from here, you are going to get 1. So you're going to get this line, but at 0. But it says, oh, if the number you put in 0, the function return is 0. So now the graph jump to that point. And then the third part is if it's the number you choose x is less than 0 on this side, then the function is explicitly say it returns then the number is minus 1. Okay. And you want that with this graph. Come in pieces because the rules come in 3 segments. So you come in 3 pieces of graph. This in mathematics they are called piecewise functions, and we use these techniques to a lot of time to come up with examples that for different purposes. Okay, and these are the graphs which you should know, look over and think about how the shapes, and we're going to use these all these graphs. Quite often. Hey, that's it. And have a good day. Bye bye. Bye bye.